Soil Moisture and the Urban Heat Island Effect. This was prepared by me, Mariama, and my research partner, Pranitha, under the guidance of our mentors, Mr. Femi and Dr. C.
Starting off with our introduction, the urban heat island effect is when temperatures in urban areas are higher than the temperatures in surrounding rural areas. However, not all cities are affected in the same way. Coastal cities can have a moderated urban heat island effect because coastal water bodies may cool surface temperatures. Inland cities, on the other hand, may experience larger daytime temperature variations as a result of the urban heat island effect, because the lack of water bodies in inland cities can serve to intensify heat retention. Soil moisture is something that may be impacted by the urban heat island effect. Soil moisture is the amount of water held in the spaces between soil particles. As the urban heat island effect raises the temperatures in cities, evapotranspiration rates also increase, which leads to a decrease in soil moisture.
Our research study is focusing on two questions. For our first question, we are going to compare the soil moisture and surface temperature in a coastal city, Toledo, and an inland city, Bowling Green, to determine if there is a difference in soil moisture. And for our second question, we will look at the soil moisture from an inland city in two different sample locations, one in an area with vegetation and one in an area without vegetation, to determine if there is a difference in soil moisture in those locations.
Our hypothesis for our first research question is that the soil moisture in the coastal city, Toledo, will be higher than the soil moisture in the inland city, Bowling Green. We are assuming that the water body near Toledo will have a cooling effect on the surface temperatures and thereby increase the soil moisture. Our hypothesis for the second research question is that the sample location in Bowling Green with vegetation cover will have more soil moisture than the area without vegetation cover.
This is a map of our coastal city, Toledo, Ohio. Toledo is located near the western Lake Erie Basin.
This is a map of our inland city, Bowling Green, Ohio.
Oh. For our methodology, we are using data collected by the SMAP, or Soil Moisture Active Passive Satellite, which we access through the GLOBE database. The gravimetric soil moisture in Toledo, Ohio will be collected from February through April of 2017 and 2018, while the gravimetric soil moisture in Bowling Green, Ohio from September through November in 2017 and 2018. As we mentioned previously, this study will also look at the gravimetric soil moisture at two different study sites in Bowling Green, Ohio from 2017. The first sample site will be soil taken from near a parking lot, which does not have vegetation, and the second sample site will be soil taken from an agricultural field, which does have vegetation. This data will then be graphed, and a t-test will be used to determine if the difference between the soil moisture and the different locations is statistically significant.
This graph is showing the gravimetric soil moisture at the University of Toledo from 2017 to 2018 in the months of February through April. The highest recorded soil moisture was 0.34.
This graph is showing the surface temperature data at the University of Toledo from 2017 to 2018.
This graph is showing the gravimetric soil moisture at Bowling Green University from 2017 to 2018 in the months of September through November. The highest recorded soil moisture was 0.38.
And this graph is showing the surface temperature data at Bowling Green University from 2017 to 2018.
This graph is comparing the average gravimetric soil moisture content at the University of Toledo and Bowling Green University from 2017 to 2018. The average for Toledo was 0.1765, and it was less than the average for Bowling Green, which was 0.2114.
When we conducted a t-test, we received a p-value of 0.014. Since this is less than 0.05, it indicates that there is a statistically significant difference between the gravimetric soil moisture content in a coastal city, Toledo, as compared to an inland city, Bowling Green.
We noticed that the surface temperatures at Bowling Green, Ohio were typically higher than the surface temperatures at Toledo, Ohio. despite the fact that surface temperatures at Bowling Green were taken during autumn months, from September through November, while the surface temperatures at Toledo were taken in spring months, late February through April. Although spring is typically characterized as being warmer than autumn, Toledo's cold spring could be a result of the cooling effect Lake Erie has on surface temperatures.
Higher temperatures lead to higher rates of evapotranspiration, which is supposed to decrease soil moisture. However, the soil moisture at Bowling Green is higher than the soil moisture at Toledo, despite the temperature being higher at Bowling Green. This could be because the average surface temperature at which soil begins to lose moisture is around 30 to 40 degrees Celsius, and the highest average temperature at Bowling Green was during November of 2017, with 26.19 degrees Celsius. Therefore, soil moisture likely did not decrease at Bowling Green because temperatures were not high enough for the soil to lose moisture.
Now we are looking at our second research question. In this graph, we are comparing the average gravimetric soil moisture in an area without vegetation coverage, which is the soil located near a parking lot, and an area with vegetation coverage, which is the soil taken from an agricultural field. The soil from near a parking lot has less soil moisture than the soil that was taken from an agricultural field.
When we conducted a t-test, we received a p-value of 0.023. Since this is less than 0.05, it indicates that the difference between the gravimetric soil moisture in an area without vegetation and the area with and an area with vegetation is statistically significant.
The soil moisture sample taken from an agricultural field was higher than the soil moisture in the sample taken near a parking lot. This result was expected because the agricultural field had vegetation, and soil moisture is higher in areas with vegetation, as the roots of plants help to hold water in the soil, which prevents water from evaporating as quickly.
Here are a few of our references that we used for this project.
One of the challenges that we faced while conducting this project was that we were unable to find soil moisture data for certain locations, such as Madison, Wisconsin, or certain time periods, such as specific months, from the GLOBE dataset. Another challenge was the short amount of time that we had to come up with a research question and prepare a presentation about it. One of the best features of this internship included being able to conduct our own research about a topic that we were curious about. Another was learning how to access the GLOBE database and being able to create an interactive project on ArcGIS.
We would like to thank our C's mentors, Mr. Femi and Dr. C, for all of the help they gave us in coming up with our research question and determining the best ways to go about collecting our data. We would also like to thank the C's program for giving us the opportunity to spend our summer learning from this internship. Thank you so much for listening to our presentation.